Greetings and welcome to a new video about diode circuits, and in this video I would like to discuss the application of diodes in rectifier circuits. We will look at the different type of rectifiers. In this case we will also look at the full wave rectifier and half wave rectifier, and also work out of course the calculations for the full wave rectifier in the bridge and the center tapped configuration. So we see the calculation, also the verifications in the SPICE simulations. So let's first discuss the outline of this video. We have the half wave rectifier. We'll discuss that and then work out three different examples. Example 1.1, example 1.2a and 1.2b. We see the effect of the barrier voltage of the diode and also the ripple voltage for large output capacitor and also for small output capacitor. Now for the full wave rectifier we'll do that similar, and then for the bridge rectifier we will look at the effect of the output capacitor, also the ripple for small and the large capacitors. In a similar way we'll look at the center tap configuration for a full wave rectifier. That is actually our outline, and we see here that we have 7 examples. Okay, let's see. First we start with the half wave rectifier. This is the circuit for the half wave rectifier in the positive phase, or the positive part of the input voltage. Input voltage is Vin. This is the diode D1, and this is considered to be a load RL. The current here, given in green, will flow because the voltage for the Vin is positive or larger than the Vd on. And if I look at it in ideal case, if this is larger than 0, the diode will conduct. And that is the part here at the output in red from T0 to T1. But if you go to the next phase, by the way, the input voltage is then given by this expression, where the Vp is the peak voltage in the sine of omega t, where the omega is the radian frequency. Now, if the sinusoidal input voltage is positive, the diode is forward biased. That means the conduction is there and there is current flow in the complete circuit, and there will be also current flow through the resistor. So that means we have voltage drop across the resistor and also the current flow, of course. Now, if you have the next part of the period, which is then the second period, which is from T1 to T2, which is negative, then the polarity will be then reversed. Now the diode will not conduct, it will then be reversed biased. So the current in here will be 0. So there is no current flow here, and you can see this part is what we have before from T0 to T1. Now from T1 to T2, the output is 0. So we will measure 0 volts across it because there is 0 current. So if the sinusoidal input voltage is negative, the diode is reverse bias, or it will block the current flow, no current through the load resistor. That is the basic configuration or the basic mechanism of the half wave rectifier. Of course you can reverse this diode and you have then the inverted part of it. So then will be then the first part will be then blocked and the second part will be then conducted. This is then the complete picture. You can see from T0 to T1 to T2, etc. So it will repeat itself. You get only the half wave, which is then passed, and the second wave will be then not passed. That's also what's called the half wave rectifier. Okay, now the average value of this signal is most of the time very important, because we are not interested in the instantaneous values, and that's given by this area, which is the peak value here, and the V out average is this value for this green part of the area, and that calculation of that is using integrals will result in Vp, the peak value of your input voltage, over pi. That is when we consider the diode to be ideal. If it is not the case, for example, if it has some 0.7 volts drop, then you need to adjust this Vp as Vp minus Vd on over pi, and you have then the more correct or more exact expression. The RMS value is also very important, especially for dissipation in the loads, and this is given by this expression. So V out RMS is equal to the peak voltage of the input voltage divided by the 2, and again assuming the diode has 0 voltage drop when it is conducting. And when it is not conducting as perfectly, so we have some voltage drop, we have then Vp minus Vd on, which is then 0.7 volts, again as a constant. Okay, those are 2 important formulas you can use when you work out power conversion or the power electronics calculations. Now let's look at our first example and look at the effect of the barrier voltage of the diode. We have an input voltage here, which is given by 4 up and 4 down, so 4 volts peak, and has some frequency, and this is then given by this expression. So V in is equal to 4 sine 100 pi t. What we want is to determine the output waveform. Now, since we know the diode will block or will have 0.7 volt drop across it, which is called VD on, if this is 4 volts, you will lose 0.7 across the diode, so you will only have 3.3 volts as the peak value. That's shown here, so it starts at 0, going to 3.3, and then it is 0 again, and then the second half of the period, which is this part of the input voltage, the output will be 0, and that is the situation for half-wave rectification. And the frequency here is 50 Hz. You can see that by 100 radians per second over 2 pi. Okay, that is the effect of the barrier voltage of the diode when this is 4 volts peak. But when you change that to, for example, 100 volts, and the same circuit, same values, everything is the same, only the peak value is changed, then the output waveform will look like this. Again, you lose 0.7 volts in the conduction phase, so you will get 99.3 volts. But now you can see that this is closer in percentage to the 100 volts than this 3.3 to the 4 volts. So you get in percentage more accuracy. That's also the case if you have very high voltage applications. That 0.7 or maybe 0.9 or 0.8 volts loss is not really that a problem. So in this case, the input voltage is 100, same frequency. Now you can see this as a percentage is not a really big problem here, the 0.7. But if this is, for example, 2 volts, then it is a huge problem, of course. Now, looking at the simulation results, again, the same 2 circuits. This is the first part where you have 4 volts peak. You can see the circuit here, and we have only 1 k ohm as the load resistor. The blue one is the input. You can see it goes up 4 and minus 4. And the red one is the output. You can see it is maximum 3.335. So let's say 3.34 volt. It's not 3.3 again, because the diode here is modeled as a little bit more accurate than just a 0.7 volt drop. So you will have a little bit a difference in the results here. If, for example, the load resistor was large, for example, 1 mega ohms, the current flow through the diode will be also much smaller. And then the voltage here will be also a little bit smaller because the diode will be then, or I mean larger, because the diode will be then has less current through it. So you will have less current loss in the diode. That really depends on the circuit configuration. So you can never say it is always 0.7. Okay, the next one is here. And you can see the blue is again the input, but the red one is almost on top of that blue. Of course, the second phase is just 0. What you also see in the previous result from simulation is the red line, which is the output, is not starting as at the beginning as the blue one. So it has some delay. And that is required because it needs to charge up this input voltage to 0.7 volts. That needs some time. And then the diode starts to conduct after 0.7 and larger. That's the reason why this is a horizontal here and also here. So if you go under the 0.7, the output will be then also 0. So there's also some delay here, and that is not taken into account also in our calculations here. So this all taking as an ideal case. In this case, we see that the delay is not really that big problem because the voltage is very large compared to the first case. Okay, that's for this example 1.1, effect of the diode barrier. Now we look at the effect of the output capacitor. Now this is very important because the output capacitor, which is shown here, the exact same circuit, actually only addition of a parallel capacitor across the load, will make things a little bit different and also make the output more horizontal, which is of course what we want, because we talk about rectification. It is not actually that you have some part of your sine wave at the output. It's not rectification, it's just a part of your input to the output translated. Now the first case, let's look at it in a step-by-step format. In the first case, we have actually the following. If the input voltage going from T0 from 0 volts up to the peak value, the diode will conduct and the capacitor will be charged. So diode is forward biased, Initially, the charging of the capacitor will be take place, and so you can see the charging of the capacitor here. It will go up to Vp minus 0.7 again, because the diode will let's say block 0.7 volts. Note, this happens only once when the power is turned on. So this part of the graph for the output is only at the beginning, not in the let's say the repeating cycles of your output. Now, this is for the first part. Now, if you go from this all the way to the second part of phase, also actually the 75% of the waveform, from the peak to the T1 and from T1 to T2, the following thing happens. If you go down, because the capacitor is charged all the way to Vp minus 0.7 volts, if you go down, the capacitor voltage is now here larger than the voltage which you apply here as a Vin. That means the diode will be then open, or it will not conduct, so it will be reverse biased. So the diode is now reverse biased, actually from this all the way to this part. So the capacitor is now discharging its charge, the charge it has collected here from the first case, through the resistor here, and that is shown here. So this curve is first part, and this is the discharge curve for the second part of this graph. Now, this will continue, and discharge continues while the input voltage is smaller than the output voltage, because when you have an open circuit here, the charge will be then flowing, or the current will be flowing in this fashion. And when this is larger, the Vin, then the voltage at this node, then the capacitor will be again charged. And that is actually the next stage, because when the Vin now exceeds the Vc, which is some value, at for example this part, then it is again charging. So that is actually this part. So that is actually repeating. So this first part here is only when the power supply is turned on, and then it repeats itself in this fashion. So with this part, from this to that part, going down, and then going up and going down, that will repeat itself for the other part of the period. So you have then the forward bias of the diode again in the third case. The capacitor is now charging and back towards the peak input voltage, minus of course that 0.7 volts. It goes towards that, but it is not reaching that value, because they have a 0.7 volts you lose across the diode. And the charging continues while the input voltage is larger than the output voltage. That is really important. Okay. We move on, and let's also look at an example effect of the output capacitor, and then the ripple voltage, because ripple, we have discussed that it is a very important consideration for your rectifier. Now the ripple voltage, or VR, is the variation in the capacitor voltage or the resistor voltage due to charging and discharging. So because of this charging and discharging, so this part is charging, this part is discharging, this part is again charging, you have a maximum and a minimum value. And the difference between those two is the part what you call the VR. And the ripple voltage is not really desirable, so we need to make it small. The smaller the ripple, the better the filtering. So if I have this as an example, so I will make it, I blew up actually this part and then repeat this for several cycles. You see this part has the peak value here and the minimum value there. So the max and the minimum value, this is called the VR, which is quite large if I look at the peak here. So in this case, less effective filtering and larger ripple voltage. But if I have another example, which is shown here, and this is caused by different configuration or different component values, and now you have this VR again, and now you have more effective filtering, and it is smaller ripple voltage. So the ripple voltage is given by this expression, which is an approximation. If this line is sort of a little bit linearly decreasing, and that's given by this is the Vp, the peak input voltage value for the Vin, minus the voltage drop across the diode, which is called Vdiode, 0.7 approximately, the F, the frequency of operation of your input signal, the load resistor, and the capacitor. What you see is the ripple voltage can be decreased by increasing the frequency, or the load voltage, or the load resistor and the capacitor. So these will make that, if you increase that, the VR smaller. So making a larger capacitor, for example, if you place that as a parallel, then you will make your ripple smaller. If the Vp and the diode, etc., are all fixed, because you cannot change always the frequency, and the load is fixed most of the time, and the diode is also fixed, so the frequency and the peak value of your input voltage is also fixed. So only thing you can adjust as the designer is the capacitor value, so you can then lower that. The F is the frequency of the input voltage, and also the Vp is the amplitude. But you have also the VDON, which is also shown here. But more accurate, or more, let's say, exact expression here is this. By the way, this is an approximation which follows from the exponential relationship between the current and voltage of the diode, because this is not really the actual situation. This is only valid when the ripple is really small, when it's going here linearly down. This is also linearly down, sort of, but it is actually an exponential decrease sometimes when the peak ripple is really large. And then you can use better this approximation. It looks similar to that one, but then the second part is actually an exponential decay, which we need to take into account. Okay, now let's use this and then take a look at the situation where we have a large capacitor. So a relatively large capacitor. We have a load of 1K, 4 sine 100 pi t as the input voltage, as shown here again. This is a diode. The capacitor here is 100 microfarads, and the diode D1 here is 1N4007. That is the type we will use. Okay, let's look at the ripple voltage for this case. First, the calculation now. Very rough approximation. We already said that this is the ripple voltage approximation. If I substitute everything in here, 4 minus 0.7 over 50 Hertz, because this is 100 pi over 2 pi, will be then the cyclic frequency, which is 50 Hertz. Our load is 10 to the power 3, 1K ohms. And we have also 10 to the power minus 4, which is then this capacitor. And it will give me 660 millivolts. That's for the ripple voltage using this rough approximation. When you do a little bit better approximation, which is then a more accurate result using the exponential, you will have this expression. Now, if you now substitute the values in here, you will have these, and the result will be then almost 600 millivolts. So you can see it is quite some difference, 62 millivolts between the rough approximation and the more accurate approximation for the ripple voltage. But let's also look at the simulation, because that is also nice to see what's really happening there. The blue line is again our input, and the red one is the output. You can see the first charging part, and that is only the first case as discussed, and then you get the repetition of the charging, discharging. So it is charging, discharging, charging, discharge. That's the capacitor effect. The maximum value of this red curve is 3.32 volts, and the minimum value of the output was 2.8 or 2.80 volts. So if I now look at it, the maximum minus the minimum, so from a simulation I get 520 millivolts, which is, this one is more closer to the approximation I have from this more accurate formula than this rough approximation. It is still some difference, approximately 78 millivolts, but it is closer, and this is definitely farther away than this one. So that depends really on also how much ripple you have. And in this case, the ripple is 600 millivolts, 500 millivolts approximately, which is, looking at the peak value in percentage, quite large. Okay, that's for this first example. Now let's all look at the exact same circuit, but then having a small capacitor. So I don't only change the capacitor from 100 micro to 10, and everything stays the same. So the input, frequency, everything. What happens then? Now let's also look at the calculations again. We again have the same calculations. The only change is the 10 to the power minus 5 for the capacitor. So it's not 10 to the power minus 4. Now you get 6.6 volts. That is actually kind of a ridiculous thing, because how can you have a ripple of 6.6 volts where the peak is just 4? So that is definitely invalid. Now we need to definitely use the better approximation here. So the rough approximation is not valid here. It's not even an approximation, it is just not valid. So let's then use this and then substitute the values in here for the capacitor, the new one. Then you will get 2.85 volts. You can see the ripple is increased from approximately 600 millivolts to all the way to 2.85 volts. It's quite a change, quite an increase. Now look at now the simulator. You can see this is definitely not a linear decrease. It is kind of an exponential decay. The red one is again the output. So you can see the maximum output is 3.35 and the minimum is 0.732, so 732 millivolts. Now, if I now do again maximum minus the minimum for the output, I will get 2.62 volts. This value is much closer to the value we have calculated from the better approximation using this exponential formula. So this rough approximation again is definitely not correct here. So what we have seen now in this example 1.2a and b, by changing the capacitor, so making it smaller, you definitely make your ripple larger when you go down in the capacitor. And for your approximation or your calculation of the ripple, you really need to be careful when you want to have more accurate result in your calculations. And that is using this exponential decay formula. Okay, that is for this analysis. Now we go to the next chapter, which is in the full wave rectification. This is the circuit you have here, which is Vn. It is not always connected by a transformer, but most of the time it is done. You can see it is 4 diode configuration and it is a bridge, so that's why it's also called a bridge. And then we have a load here, which is RL. This could be also again an RL in parallel with the capacitor. That could be the case. One of the advantages of a full wave rectifier over the half wave rectifier is that you rectify each half of the period. That's why it's called a full wave rectifier. So the full wave will be then rectified. Okay, so requires 4 diodes, this circuit, and during the positive half of the input cycle, you will have that D1 and the D2 will be forward biased, and D3 and D4 will be reverse biased. And that is actually shown in this configuration or the drawing. The green are meaning that it's on and the pink one are off. So the current flow is the pink one. You can see in the positive part of the input voltage, which is then this part, the positive part. The transformer will then replicate this here with some ratio. Let's say it is exact same. Then this current flow will be in this direction going through D1, but D2, D4 will block. Of course, it is reverse bias. It goes through the load, the ground, but there's also ground here, so it will then pick up here, going through D2, not through D4. Why? Because this potential is larger than that potential, because this is ground. So this is again reverse bias, and then going here, and then make this full circle again, and then the situation repeats itself. This is for the positive half of the input voltage. Now, during the negative part of the input voltage cycle, you have then the reverse. So D3 and D4 are forward biased, but D1 and D2 are reverse biased. And this is shown here. And that is then the next phase. So this is then reversed. So the polarities are reversed. You can see the polarities for the transformers also reversed. The current is also reversed. But what you see is the current is always flowing from top to bottom for the load. So that is not really flipped. And that's why you have this configuration at the output. And this is the output voltage, which is called the rectified, full wave rectified output for the bridge configuration. The average value of the output voltage is given by this, so it is twice the average value of the full wave rectifier. Again, if you have a voltage drop across the diode, which is there, but you will lose now, in this case, 2 diode voltages, which is then 2 times VD on. That means 0.7 times 2, so you will lose 1.4 volts in the numerator here. So that's the more accurate result over pi. If you use the ideal diode model, this is the formula you can use. And this is then the graph you have. Of course, you have now 2 parts of your area, and this is the V out average having this value. All right. Let's look at an example, 2.1a. Again, we look at the effect of the capacitor, and that is the ripple voltage. We have now the V in here, the transformer. This is the primary part, VP primary, and we also have the secondary part. The turns ratio are 5 to 1. That means this voltage here is 5 times the voltage of the secondary part. So if I apply here 50 volts peak, you can see that. That means 10 volts peak here at the secondary. The capacitor is again 100 micro. The load is still 1K, and the diodes 1 to up to 4 are 1 and 4007. The same diode type I have discussed and used in the half wave rectifier. This is now a large capacitor, so relatively large. And we have now N secondary over the N primary, so this is the turns ratio of your the transformer is 1/5 or 0.2. Okay, let's now calculate again the ripple voltage calculations. The rough one is this. So I said already, this is now the ripple, and you have to now subtract 2 times the VD on, because the diodes, we have 2 diodes we need to overcome. And you divide now by the 2FRLC. Why? Because the period is not 1 over F anymore, but it is 1 over 2F now, because the period is now 2 times smaller for the output voltage. Now, if I now substitute the values, it is 10 because 50 is the input, and I go from 50 to 10 because it's 5 to 1, so I go by a factor of 5 down, and I have now 2 times 0.7, it's 1.4, and if I now substitute values for the capacitor, resistor, and the frequency, etc., I will have 860 millivolts for the ripple. Peak, that's always peak. Okay, if I now go to the better approximation and use this, you can see that the VP secondary minus the 2 times the VD on and the exponential decay formula. When you substitute this, you will have 818 millivolts. So a little bit smaller, but more accurate. Now, when you look at the simulation, this is the input, the blue one. You go 50 up and 50 down with some specific frequency, which is then 50 Hertz here. You can see the first part is charging. And again, it has some delay. It is not starting right away at 0, but it needs some time because you need to overcome that 1.4 volts of 2 diodes together. Then it is charging, it charged at the maximum value and then decays, and then charge again and decays, charge again and decays, etc. So this is the circuit, and this is the maximum value, which is 8.56, and the minimum is 7.94. So the simulation result, this is the input and this is the output. So the simulation result will give me then 620 millivolts. So this is a little bit lower than that one. So you see approximately 200 millivolts off. But it's better approximation than that 860 millivolts. Again, it is not exactly. Why is this not exactly as this one? There are 2 reasons. First is the diode is not exactly 0.7. But the more important reason is this F what we use is the period. 1 over F is the period, because it is from this point to that point. But which is not true, because this point to that point, so from the maximum value to the minimum value of that, let's say decay, is not the half the period. It is a little bit smaller. You can see that. This is the peak, but this is actually starting to increase again before this part, which is then the half of the period. So I need to make this 1 over F actually smaller, and then you will have more accurate result for your ripple. But this is good enough. You don't know, of course, how much this is. You need to have a more accurate calculation for that, but for the first order approximations, this will do the job for most cases. Now, we have now this situation for the large capacitor for the full wave rectifier with the bridge one. We move on and then make the capacitor again 10 microfarads instead of 100. Again, the same circuit, everything is the same. Input voltage, the turns ratio, and we need to calculate again the ripple voltage. So let's go then through the calculations. Now 10 to the power minus 5 instead of 10 to the power minus 4. Now you get 8.6 volts, so that's kind of a really large value, because you get 10 volts peak, and then minus this, there will be then 8.6 from this, so it is kind of a ridiculous value, so it is also invalid. So this is again not possible for this part or for this situation. Now the better approximation, we need to use that exponential part again, and that will give me, if I substitute the values, 5.44 volts. Quite large if I look at the output, which is approximately 10 for the secondary part, and then I will lose, of course, 1.4, but this is in percentage a really large value. Okay, this is simulation. You can see that the red one is the output. You can see the peak, maximum, and the minimum for the output, and this is the input, the blue one. And this is a circuit in the SPICE simulator. 8.62 volts is the maximum, and the minimum is 4.63. So you see here approximately peak of 4 volts. This is the input and output. So you see 3.99, let's say 4, but it is still off. So it is 1.45 volts difference between the calculations here from the better approximation and the ripple voltage we have determined from the simulator. Again, the reason is there is some change or some slightly error in the voltage drop, because we expected here it was you can see that 7.6, not 7.6, so you'll have actually 20 millivolts here, but that's not really business. The actual situation is that this peak maximum and the minimum value is not a half of the period, but is smaller. And again, that needs to be determined very accurately, but first order approximation will do the job here, but you need to accept or be aware of the error you make by taking only 1 over the 2f, which is not correct because the period is smaller. Then you have this approximation and you will see that this is 1.45 volts off. Okay. Now let's also look at the full wave rectification, but then for the center tapped, because you have now a transformer here and the center is tapped and then grounded. Now in this case we have only 2 diodes, and I will make this drawing it's more accurate so you can see the V primary and 2 times the V secondary, but they are the half of the primary reflected to the secondary. So the complete is here, the secondary voltage will be exactly divided by 2. And this is the center tapped part grounded. So it requires 2 diodes, but also a center tapped transformer. You always need a transformer for this configuration. For the full wave rectifier with a bridge, you might also do that without a the transformer. Now you need the transformer. Now during the positive half cycle of the input voltage, the D1 is on, but D2 is reverse bias, and that's better shown here. So you can again see the current will be flowing here. D1 is on, but D2 is off because it is negative. If I look at now the negative half cycle of the input voltage, now the reverse situation is happening. Now you get this situation. Now the result is exact same as for the full wave rectifier with the bridge configuration, but you need only 2 diodes now, and also you need a transformer with the center tap. So those are the let's say the differences between the 2 configurations, but the result is the same. Now the average value of the output voltage is again the 2 times the average value which you have for the half wave rectifier. One advantage of this over the bridge is that you don't do 2 Vp minus 2 times Vd on, but 1, because you only have 1 voltage drop you lose here in this case. So that's kind of an advantage. So I have actually then this one, and it is then a little bit larger compared to the full wave rectifier for the bridge circuit. Okay. Now let's now look at the example 2.2a. Again, the same configuration, and this primary winding of the transformer and this secondary winding of transformer has a ratio of 5 to 1. So this has 5 to 1, this part, and this also 5 to 1. So if I have here 50 volts, I have in total here 5 times small, which is 10, and I also divide this by 2, so I will have 5 volts here and 5 volts there. Now that's also shown here per transformer. So we actually have 2 transformers here in one figure. Okay, again the same capacitor and the resistor value, and also the input voltage with the frequency of 50 Hertz. So we need to calculate the ripple voltage, again rough approximation, but now we have 0.5 times the Vp secondary, because it's only the part here, and then only 1 Vd on, because you only lose D1 or D2 depending on the cycle. Okay, this part is still the same. If I now substitute, because this is 0.5 times 10 is 5 minus 0.7 divided by the values, you will get 430 millivolts. Looking at the better approximation, with the exponential decay, you will have 409 millivolts, so a little bit lower to 21 millivolts. Now looking at the simulator, the blue one is the input, the red one is again the output. This is the circuit in the SPICE simulator. You see here 200 milli, that means actually 1 over 5, so the output divided by the input, that is actually the winding, output winding divided by the input winding. And now we see the capacitor and also the resistor value, but if I now look at the maximum and the minimum, it is 4.31 and 4.00. So it is, looking at the input and output voltage, the simulator will give me 310 millivolts. This is, again, a little bit smaller than this one, so you will have an error of approximately 100 millivolts. So it is 91, but it is closer than that one. And again, the differences lies in the value of the voltage drop across the diode, and also the actual period between the maximum and the minimum, which is not 1 over the 2F, but it is a little bit smaller. Okay, this is for the case where you have the large capacitor, which is 1 microfarad. Now we will look at the exact same situation where we have a smaller capacitor, so 10 times smaller. Everything is the same as in example 2.2a. Let's look again at the calculations. We go a little bit faster because we already seen that. Only thing we change is the capacitor. So now we have 4.3 volts. So that's kind of a really large ripple, which is not really possible. So the better approximation need to be used because we have a very large ripple here, which is not really logical, or it is invalid. So we have this formula again, the exponential decay. If I now substitute the values in here, I have this expression, and this will give me 2.72 volts as the peak ripple across the load. Now look at the simulator. We have the maximum. The red one is the output, the blue one is the input, 4.34 and 2.36. So now the maximum is the input and output voltage. The simulated result will give me then 1.98, let's say 2 volts. So I have now 74 volts, 740 millivolts difference. Again, the difference is really due to that period we use here as 1 over 2F, which is larger, and we have a smaller period here. And also some differences between the voltage drop across the diode, which is not 0.7 always. Now this is now for the second example, 2.2b, about this center tap configuration of the full wave rectifier, but now with a small capacitor. So in general, you see when you make this capacitor smaller, your ripple will be larger, and for the bridge rectifier and also for the center tap rectifier, but also is valid for the half wave rectifier. But only for the full wave rectifier you rectify the full wave, and for the half wave rectifier you only rectify one of the waves. Alright guys, this is for this example set of the rectifier circuits using diodes. We have discussed the half wave, the full wave rectifier, and 2 configurations, the bridge and the center tap. If you have any questions about these discussions and the examples, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.